Hey everybody, last installment for this chapter. What I need you to do is turn your packet to page 4, the front of page 4, that will look like this. Quick thing we have to cover first is this concept of a karyotype. I mentioned it in the last video where I showed you what sex chromosomes were, but I would like to identify and define the two terms that are on your notes. It's autosome and sex chromosome. An autosome is going to be classified as anything that's not a sex chromosome. It will have nothing to do with gender. What you have is, on this karyotype, the ones that are numbered 1 through 22 are all classified as autosomes because they're identical. Both male and female will have 2 copies of each of those numbers in homologous matches. Every gene that we've dealt with up until yesterday was really understood to be on one of those 22 pairs because males and females didn't matter. It wasn't until today when you had to really read into the fact if it said male or female with sex-linked problems, because the other pair, that 23rd pair, is going to be classified as a sex chromosome. A sex chromosome, some students will get confused with what a sex cell is. A sex chromosome is a chromosome that determines gender. A sex cell has only one pair of homologous chromosomes in it, which is a sperm or an egg. So even a sperm or egg, which is a sex cell, has 22 autosomes and 1 sex chromosome. That's what will determine if it's a male or female. So if you look at the karyotype that's on your diagram, look at that 23rd pair and identify that there are 2 different size chromosomes. That's an indication that you're dealing with one X and one Y. The larger of the 2 is going to be the X, the smaller of the 2 thus would then be the Y chromosome. So this is a karyotype of a normal male, quote-unquote normal, because it has 46 chromosomes. They're in replicated state. That's your normal diploid number for a human. If you want to look at something, many disorders that some of you have to research for your project are classified as abnormal because they have a different number of chromosomes. Like, for example, search YouTube, or not YouTube, but search the internet for something like Down syndrome, and do Down syndrome karyotype. And you will see that it looks different than the normal 46. They might highlight, if you look at the 21st pair on a Down syndrome karyotype, now do that, and compare what this one looks like versus the one that you research. Other disorders that will have an abnormal karyotype will be something like Turner syndrome or Klinefelter syndrome. But things like cystic fibrosis, that's not caused by having extra chromosomes. Cystic fibrosis is a gene within. So a karyotype can't always determine if you're going to have a specific genetic disorder, but it can determine if you have some chromosomal abnormalities, which some of you will be researching and showing to the class when you kind of lay out your genetic disorder projects. So that was something quick that I wanted you to look at and be able to interpret. You'll notice on the diagram as well that it goes in size order from largest to smallest. You will have some practice, you'll do a lab or activity that deals with karyotyping. What the focus of today's lesson really deals with is a pedigree. And a pedigree is simply a family tree that is going to trace through a specific trait. And so what we're going to do is 3 different types of patterns of inheritance. This first one is going to be classified as an autosomal, which is the adjective form of an autosome, saying that the trait that we're looking at is found on an autosome. It's not found on a sex chromosome. So therefore, males and females will have the same probability of inheriting this disorder because they have 2 copies of both. Males don't have a disadvantage or an advantage, neither do females. It's basically everything that we've been leading up to this point has been autosomal. So this is an autosomal recessive. Now, some things that you see here is how to interpret it. You see squares and circles. The key to this, and maybe you should pause it right now and draw this out. I'm going to pretend that you have the ability to pause it so you can see it right now and write that down. Now come back to me and I'll go through what everything means. A square represents a male. A circle represents a female. This connecting line that directly connects a male to a female would be a marriage line or mating line, because when you drop down from between the mating line, these are all their children. So this pair, male and female, had 3 children. A son, a daughter, and another son. So 2 sons and a daughter. This family had only 2, 1 son, 1 daughter. This child out here is not directly related. This has been married into the family. So this son has married or had mated with another female and had their own son. So this is the grandson to these grandparents, okay? Here you have a difference. What is this connection? This is actually twins. Sometimes you will see distinction between identical and fraternal. Right now they're more fraternal. And identical, sometimes they'll draw a line up here to identify them as identical. But you also notice some of them are shaded in. I've colored them in. You know, I didn't have that much time to really fully shade them in. But many of them are shaded in, others are completely empty. A shaded in person says that it's affected by a disorder. Or something, whatever you're tracing, it's affected by it. So I've identified this as an autosomal recessive pedigree, because these people are affected by an autosomal recessive genotype. Autosomal meaning that men and women have the same number of genes. So if I choose any letter, I'll choose A to make it simple. I'm going to show you that this has to be an autosomal recessive disorder. If I look here, I can produce the genotype little a, little a. Because they exhibit the phenotype, there's only one variation of genotypes that can be autosomal recessive and have this effectiveness. So everyone that's affected, I'm going to say, has the same genotype. Because they all are affected by the recessive phenotype. Therefore, what is automatically, anyone who's not shaded, guess what they have to have minimally? Hopefully you're thinking it has to have a dominant A. They wouldn't be unshaded if they didn't have a dominant A. So you can fill in the dominant A for all of them. What we're now going to do is go back in and fill in as many of these lines as possible. So there's a few that we have to work with. If you notice and know the inheritance pattern, if your father has little a, guess what every one of their children have to have inherited from the father? If these are legitimately their children, his child, they have to inherit a recessive A. That's all he has to pass on. So you can assume that they have to be the heterozygous form. They got the dominant from their mother. The father doesn't have the dominant to pass on. So they must have got that from father, this from mother. So we've guaranteed, we filled in their full genotypes. What about the mother? Is there anything from their children that can give you enough information to identify what the second allele must be? Think about that. If you said, well, there has to be a recessive here, you are correct. And why does it have to be a recessive? Because of this child. This child got one recessive from the father. He did not get both of them from dad. That's not how you inherit alleles. You get half from your dad, half from your mom. So where did this other allele come from? Had to have come from mother. So she has to be heterozygous as well. So look right here. Is there enough information in their children to determine what he has to have? I don't think there is. Because neither one of them are affected, you can't really look to them and say, well, they had to inherit something. You could only assume that she has a dominant A. So what you can do is actually do a slash and a dash. And what that says to me is you've looked at it, you've basically been not able to determine what is that second allele. It could be either homozygous, dominant, or she'd be heterozygous and still have these children. With this, the mother's affected, so what does that guarantee the children have to be? Has to be also heterozygous. Okay, so that filled in. What about over here? Is there enough information? When there's a lot of unaffected people here, you don't know. We don't know anything about her parents, so we don't know any information. And we don't know anything here, because he came from this crossing. There's not enough information to pin it down that it must be a heterozygous or homozygous situation. So we have 3 people here that we can't determine, but we did fill in a lot. Sometimes you have to look at this and be able to determine what the inheritance pattern is. I gave you that this is autosomal recessive. Now I'm going to give you another one, which is autosomal dominant. And we're going to work through this. Eventually you have to look at them and look for clues, but I don't think you're ready right now. So pause it, draw this for the next thing on your notes, which is on the back page, autosomal dominant. Press pause, because I'm going to start going into it now. If this is autosomal dominant, what does that tell you about everything that's unaffected here? If I'm saying that the shade, we always put it in the perspective of the shaded person. So if the shaded person exhibits an autosomal dominant trait, we can then assume the unshaded have to be showing the recessive phenotype. They're always the easiest ones to determine or work with first, because recessive gives you their full genotype right away. So once again, I'll use A's to stay consistent. I can automatically determine that those that are unaffected this time must be the recessive phenotype, so therefore they have to have the homozygous recessive genotype. So I'm going to start filling these guys in. Notice, if you have two parents that are homozygous recessive, it's guaranteed. This is sometimes a clue for inheritance patterns. If you have two parents that are unaffected here, and they have all these children unaffected, it's impossible for any of them to have the dominant allele because they don't have it in that previous generation. Over here, we have the homozygous recessive, so we go down and fill all these people in. Just like on the last pedigree, if you now know that they're the dominant form, all we know right away is that they must have one dominant allele. We're going to work through it to see if we can determine what the second allele is. So try that first. Maybe you now know enough information to do this. Try as many as you can if you want to press pause, but I'll work through it. Because this mother has only the recessives to pass on, she has to pass on half to her children. She has two sons. Both of them have to receive that recessive allele. All right, the next one down here, because she got the dominant from dad, mother only has recessive to pass on, so she also has to be the recessive. For this one, we don't know anything about her parents, so that's not going to be helpful, but her son has half a little a from dad. Guess where it got the other little a from? Had to get it from mom. So the only person up here that we don't know with 100% accuracy what the second allele is, because there's not enough here, she could be homozygous dominant or heterozygous dominant and still have children that have that genotype. Do a Punnett square. Do dominant A with recessive A, you can see you can get that phenotype or genotype. If you have a heterozygous A, you still can get that genotype as well, so it's not, you can't say with 100% certainty what this person is. Okay? So that's the autosomal dominant. I'm going to press pause because I think I'm getting near my 15 minutes, because I want to do one more which is sex-linked. So you're going to have to watch the second video. Sorry.